Okay, this is number 20 in section 3.3, and you'll notice that I wrote, this is a third of the problem. It's a very long problem, and I wrote it out just because if I actually do the problem by writing it out as I'm talking, it would take, I don't know, maybe 20 minutes of video or 15 minutes of video. So hopefully this is clear and it makes sense. So 3.3 says, number 19 says, find two linearly independent Frobenius series solutions for x being positive for the differential equation. So I'm going to go ahead and start with this page. This is page 1. So let me maybe make this a little bit, smaller. Okay, well, actually make this one bigger. Okay, hopefully you guys can see that. So here's my differential equation, and we want to write it in a nice standard form, so I'm dividing, right, 3x by every term. So I get this guy, and let me make this a little bigger. And then we have, we can manipulate this equation, right? I mean, this guy is the same thing as, right, these fractions are equivalent. Similarly, right, 2/3, 2 over 3x is equivalent to this guy here, right? And I just put a little note here, right? I mean, you can just multiply top and bottom by x. And because you want to obtain, again, that x squared there, it just makes it a very nice form. And I'm going to go ahead and follow example 4 in your book. I mean, I would literally mimic this example. And okay, so we want to find our series solutions. So what's our p of x and q of x? Right, remember our p of x is, right, I think I wrote it in blue last time, so 2/3, and there's my p of x, right, and similarly 2/3 x, and then there's my 2/3 x. So there's my p of x and q of x. And I mean, you can do it two different ways again. But okay, so last video I showed you, you basically take the limit, right, of your p of x, which just gives you 2/3, right, because the limit of a constant is a constant. But remember, p naught, right, is p of 0. So, I mean, this is our function. So if we evaluate 0 at 2/3, well, we're not really plugging in anything in because there's no variable, so that's why our function is just 2/3. But again, limit of a constant is a constant. Similarly, we have, so our q naught is q of 0. So q of 0 is, well, I mean, this is our q of x, right? This is our given function. So if we q of 0 means you're evaluating 0 at q, for this specific function. So 2/3 times 0 is 0. That's why I have a 0 here. This guy, right, that's really 2/3 times 0, well, which is just 0. And then the limit of 0 is 0 because it's just a horizontal line, and as x approaches 0, you're still at the y-axis. You're still at 0. So here, just again, this q naught is just the first constant of the, or coefficient of your polynomial function. And thus, we know x equals 0 is a regular singular point, right? Because our p of x and q of x are both analytic. So that's the first part. And whoops, let's see if I can bring over my second part. Oh, I don't know if it's gonna, yeah, there we go. So hopefully I can bring this down. Oh, sorry about that. Okay, so hopefully you guys can see that. It's not letting me just really go down here. Okay, so my top guy says, since p of x and q of x are polynomials. And notice I wrote the polynomials out. Okay, and this is in your book on page, since it's very small here, on page, oh, where do they talk about it? Page 223. This is basically what I wrote, and this is just to remind you that p of x, right, is a polynomial function, which is p naught plus p1x plus p2x squared plus, dot, dot, dot. And similarly, right, q of x is q naught plus q1x plus q2 or q sub 2 x squared plus dot dot dot. So this is equation 11 in your book if you want to look at it, since it's really small and I'm having trouble zooming in for that part. So then now we know that the Frobenius series we obtain will converge, right, for all x, or for all positive x, right? That's what that means. And so our initial equation, well, remember we have, make this a little bit bigger, our initial equation, well, we have our P naught and our Q naught, right? This was our P naught and Q naught. And then this is just algebra, right? This is just a quadratic equation. We do some factoring, and then we obtain these two guys here. So R1, well, I mean, so we have R is 0 or R is a third. And I chose R1 to be 1/3 just because we're going to be using Theorem 1 for this problem. And we want our R2 to be the smaller root. And so 0 is obviously smaller than 1/3. And note that, right, R1 is strictly greater than R2, right? 1/3 is greater than 0. And if you subtract these guys, right, you get a third, which is clearly not 0, or a positive integer, right? It's a rational root, right? 1/3 minus 0 is a third, and that's not an integer. So by Theorem 1, right, this backwards E means there exists, if you want to write it in words, two linearly independent solutions. So I'm using Frobenius here because I'm looking at part A, where it says let R1 and R2 be the real roots, we found our initial equation, and so it says there exists two solutions. So because our theorem, right, we have our hypothesis here, so if this is true, then this is your conclusion. This must be true. And again, this is basically equation 18 in the theorem, and this is equation 19. All right, and this is my R1, and that's my R2. So now we actually have to find well, we're still not finished. We still have to find our AN and BN. So I'm going to do dot, dot, dot. So this is the first part of the problem, and I'll probably do the second part in the next video and maybe a third part. Please ask me questions if it's unclear, because your homework problem 19 is very similar to this problem.